Professor Omar Yaghi is James and Nathan Chair, Professor of Chemistry at UC Berkeley. His work encompasses the synthesis, structure, and property of inorganic and organic compound and the design and constructions of crystalline materials. He is actually one of the pioneers of a several and extensive class of new materials like metal organic framework called as MOF, Covalent organic framework COF, and zeolitic imidazolate framework ZIF. These materials are interesting because they have very high surface area to date, and they are interesting for hydrogen, methane storage, carbon capture, and conversions, water harvesting from desert air, and catalysis, to mention only a few of the applications. The building block approach he developed has led an exponential growth in the creations of new materials, having a diverse and multiplicity previously unknown in chemistry. He termed his field actually reticular chemistry, and he defined it as stitching molecules building block into extended structure by strong bond. So Professor Yaghi has so many awards. I will just name few of them. He's elected as a member of the National Academy of Science of the United States, and he's honored with many awards for his scientific accomplishments, including, for example, the Materials Research Society medals in 2007, the American Chemical Society Award in the Chemistry of Materials in 2009, and the King Faisal International Prize in Science in 2015, the Royal Society of Chemistry Spears Memorial Award in 2017, the Albert Einstein World Award of Science in 2017 also, the BBVA Foundation Frontier of Knowledge Award in Basic Science in 2017, the World's Prize in Chemistry in 2018, the ENI Award for Excellence in Energy in 2018, the Gregory Aminoff Prize by the Royal Swedish Academy of Science in 2019, the August Wilhelm von Hofmann Densmünzer of the German Chemical Society in 2020, and the Royal Society of Chemistry Sustainable Water Award in 2020. So this is only a few of the example of awards. Professor Yaghi, if you would like to add a few of them, feel free to let us know. We would be glad to join you to congratulate you. So with this, I would like to just remind all participants few important points. Please, during the presentations, put your microphone in mute. And if you have any questions, don't interrupt the speaker during the talk, but wait until the end and raise your hands, and I will enjoy to let you ask your questions. So with this, please join me to welcome Professor Omar Yaghi.
Thank you very much for the introduction. I am delighted to be here. I would have been more delighted to be there in person, but hopefully this will happen soon. I want to share with you our work on covalent organic frameworks and introduce covalent organic frameworks here. In this paper in 1916, published in JACS by G.N. Lewis, and titled The Atom and the Molecule. In this paper, this is really a foundational paper that received a citation for chemical breakthroughs from the ACS. In this paper, Lewis describes how you link atoms together to make molecules through covalent bonds. or what later became known as covalent bonds. And based on those ideas, of course, we are writing Lewis dot structures in the same way that he perceived back in 1916. Today's lecture is about extending this to covalent organic frameworks. How do we build covalent organic frameworks from molecules? So the atom, the molecule, and the covalent organic framework. How do we link molecules through covalent bonds? Well, this is a Lewis structure of one of the first covalent organic frameworks made. But the reason I'm showing it here is that I would like to comment that the framework to the molecule is what the molecule is to the atom. Let me explain what I mean by that. The molecule fixes the atom in a specific connectivity, geometry, and spatial arrangement. And the molecule in the framework fixes, the framework fixes the molecule in a specific connectivity, geometry, and spatial arrangement. However, the framework also encompasses space within which matter can be manipulated and controlled. And really, it is the origin of many of the properties of covalent organic frameworks, or COFs. So in our discussion today, we will focus on the linkage. The linkage is in COF chemistry is everything, because it is really the unit that allows you to link molecules together, and it is the unit whose chemistry has to be developed to be able to make these frameworks. Now, just to give you an idea of where the field was back when I started as an assistant professor in the early 90s, this is a paper that was written by Roald Hoffman in Scientific American back in February 1993, and this is a quote from that article. He writes, "Organic chemists are masterful at exercising control in 0 dimension. One subculture of organic chemists has learned to exercise control in 1 dimension. These are the molecules, these are the polymers. These are the polymer chemists, the chain builders, but in 2 or 3 dimensions, it is a synthetic wasteland." So really there was no organic networks extending infinitely in 2 and 3 dimensions. And so the reason for that is that as you link molecules together by progressively stronger and stronger bonds, the crystallization challenge becomes more and more difficult. In other words, as the bonds between building units increase in strength, the likelihood that you're not going to crystallize that material is very high. And that's the challenge. Okay, we are all familiar with how to crystallize simple molecules through weak interactions, even extended structures that are linked by neutral Lewis-based bonds. These are weaker than covalent bonds, and you can readily crystallize these structures. Now, as your linkers or the organic ligands have charges, and you're linking them with metal ions, the charge interaction increases this bonding strength and the difficulty in crystallizing these materials. So what we've done over the years is we have overcome this crystallization challenge. We have figured out ways of balancing the kinetics and the thermodynamics of the system so that we can crystallize MOFs and the subject of today's lecture, COFs, molecules linked together by covalent bonds. So based on that ability to crystallize these structures, we summarize the progress under the umbrella of reticular chemistry. And we define reticular chemistry as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. There are 3 important things in this definition that are new to chemistry. One is the molecular building blocks being used to make solids. So we use molecular building blocks to allow us to design structures. We use strong bonds to allow us to make robust structures that are going to remain, let's say, in a power plant to harvest CO2, or in a water harvesting device, collecting water to make drinking water for many, many years. So we need robust materials that can be not just thermally robust, but chemically robust. And therefore the emphasis on strong bonds. The third component here in this definition is crystalline. We want to make these in crystalline form for many reasons, not the least of which is to be able to characterize these crystals with great definitiveness by X-ray and electron diffraction. So these three definitions create reticular chemistry and make reticular chemistry special in that it combines these three important components. And as I said, the result of this has been metal organic frameworks, which we showed in 1995 that they can be crystallized from metal ions and charged organic linkers. We also showed that for the first time that they can be made porous by measuring their gas adsorption isotherm, and later showed that in fact we can make materials that have record porosity or ultra high porosity. I will not talk about MOFs, but leave this topic and just say that it's an established branch of chemistry now, and it has gone from basic science all the way to applications and commercialization. What I want to do today is I want to focus on covalent organic frameworks, and where we have reported the first COFs, 2D COFs in 2005 and the first 3D COFs in 2007. And I also, depending on how much Adam gives me in terms of time at the end, I want to introduce molecular weaving, which combines the covalent and the strength of bonding with dynamics, and that's the report that we made for the first time in 2016. May I ask you to mute your audio? There's a lot of noise on the line, so please mute your audio. So these are the two classes of materials that I would like to discuss today. So today I will show you how we can crystallize COFs using reversible linkages and what organic chemists consider irreversible linkages. I also will show you how we can make single crystal structures that are characterizable not just by electron diffraction, but also by X-ray diffraction of these COFs, and then show you examples of how we can target a very specific COF topology and use organic chemistry and stereochemistry to put it together into a COF. Then I will show you the ultimate robust COFs that are linked by olefin linkages to make robust materials, and show you the strategies of how we were successfully able to make molecular weaving and introducing dynamics into COFs. Finally, everybody who works on COFs know that we are limited by the valency of carbon, sp2 and sp3, and therefore triangles and tetrahedra. But we have a strategy on how to extend COFs beyond connectivity of 3 and 4 to make connectivity of 8 and even infinite connectivity, as I will show you later at the end. So today's lecture is all about the chemistry. It's all about the linkage, how to target those linkages, reversible and irreversible linkages, and how to crystallize the COFs resulting from linking molecules through those linkages. This is an X-ray powder diffraction of someone attempting to link organic molecules by covalent organic frameworks. The result of that is a solid that would give you something like this. Not very much diffraction. For a chemist, we look at this and say, this is an amorphous material, highly uncharacterizable. And so this is part of the problem of why when you ask students to make extended structures by linking molecules through strong bonds, you get a lot of complaints, and of course you get a lot of spectra or a lot of diffraction patterns that look like this. So what we've done is we've tried to turn this hump, this big amorphous solid, into a crystalline structure where the diffraction lines would be a lot narrower, indicating the order, the high order of the structure. And this is where we had our success back in the early 2000s. We looked at boronic acid, and it was known that boronic acid trimerizes to make this triboroxine anhydride. And because of a CHO interaction here, this molecule, if you look at its crystal structure, is a planar molecule. So then our thinking was that since that's a planar molecule, I could try a diboronic acid. And in doing so, if I can succeed in crystallizing the dehydrated structure, then I would have made a graphitic type of hexagonal layer. And so this was sort of our guess that if you were able to successfully crystallize the result of this reaction, the dehydration reaction should be able to make a covalent organic framework. Well, this in the beginning, of course, did not work, because the student who was trying this was an undergrad, Annabelle, and she was, as everybody else, she was delivering to me X-ray powder diffractions that didn't have diffraction lines. It was all humps. And so, but in the end, we recognized what was going on in the reaction, saw an opportunity to crystallize this material. Let me describe what I mean by that. If you look at this reaction, it produces water. And when you're running this reaction, let's say at the time we were running these in a closed vessel, water is produced and it sits above the liquid. And so we realized that by controlling the amount of water above the liquid, or let's say controlling the pressure of water in the vessel, you could also control the reversibility of this reaction. And if you have the right solvent conditions to balance also the solution, the solution of water in that solvent, you're able to find the perfect conditions to crystallize this material. And indeed, this was the first COF crystallized in this way under these conditions, where we use mesitylene dioxane at 120 degrees C for 72 hours to allow the crystals to anneal and allow the crystals to grow so that you have a crystalline material. It turns out there was these conditions which are now being used or used routinely to make COFs since we published our work in 2005. You'll see in almost all the COFs that I discussed today that they are based on these conditions with slight modification in some cases, but nevertheless, these turned out to be the magical conditions that would allow you to crystallize COFs. Well, instead of that big amorphous hump, you see now very sharp X-ray powder diffraction lines for COF1. And we already had predicted what the X-ray powder diffraction should look like. This is the simulated pattern based on a hexagonal arrangement. And this is the the experimental pattern overlaid with the refined pattern. We also do spectroscopy such as IR and NMR to make sure that we have the right linkages are being formed and to assess the completeness of the reaction. So these are, I will not mention too much about this in the next set of compounds, but this is sort of the routine or the protocol for characterizing MOFs, initial characterization of MOFs, that you have a sharp X-ray powder diffraction, and you also look at the IR and NMR, in this case, boron NMR, in other cases will be nitrogen, carbon-13 NMR to assess the completeness of the reaction. So this is the crystal structure obtained from powder diffraction. It's a slipped graphitic layer, a porous structure, and it's the first COF made entirely from covalent bonds between boron, carbon, and oxygen. Well, the same reaction conditions could be used by taking diboronic acid and copolymerizing it with this hexahydroxytriphenylene and see under the same conditions, mesethylene dioxane, 120 degrees, 72 hours to make the expanded pore structure. Now the linkage is a boronic ester or a boronate ester, I guess the proper name for it, boronate ester linkage. The structure here is not a staggered layered structure, but an eclipsed layered structure. And this reminds me to mention that when you're looking at 2D infinite Kopf structures, the stacking of the layers becomes an issue. That's where you find a lot of disorder. That turns out to be one of the important, let's say, characterization challenges with 2D Kopfs, is that you know the structure within the layer, but between the layers, how they stack sometimes is highly disordered, and it requires a lot of different refinement, trial and error to actually decipher, if at all, decipher the disorder. But that's an intrinsic challenge in characterizing the 2D Kopfs, and it's an ongoing study. Now, we, in reticular chemistry, one of the things that are new, of course, is that once you figure out how to make one structure, you could use the same conditions to make what we call the isoreticular form, meaning the same topology, but with either new functionality or, as in this case, new metrics. So here the pores are 7 angstroms. From this combination, you have 16 angstroms. And from this combination, you get 32 angstroms. All of these are crystalline solids, beautiful X-ray powder diffraction, and very nicely porous structures. One of them, the COF10, the last one I showed you there, we tested and examined its chemistry with ammonia, and it turns out it takes up tons of ammonia. So 15 moles of ammonia for each kilo of COF10. We reported this back in 2010. And here a student is holding a pellet of COF10 that is filled with ammonia. And many people who work with ammonia know that ammonia is a liquid, is a corrosive liquid as used in the laboratory. And here we're holding it at room temperature and under ambient conditions, very nicely contained within the solid. So those were 2D Kopfs. To get to 3D Kopfs, you use tetrahedral building units and the same functionality to make the triboroxine ring. So now you have same conditions as I showed before, tetrahedra linked by, the linkage is a triangle, and from MOF chemistry, we know what are the best or the most symmetric structures that would result from combining triangles and tetrahedra. We have the so-called cubic carbon nitride structure, the CTN, and we have the BOR topology, okay? And we can make both, okay? This is the COF 102 structure. You can see the X-ray powder diffraction is fairly sharp, and we can characterize it using, again, the same conditions, but different building units. We can make the other topology, the BOR topology. This is the X-ray powder diffraction of the BOR topology, and this is the crystal structure using powder diffraction of this BOR COF we call COF 108, which is a 3-dimensional COF, and it's the least dense solid known at room temperature, crystalline solid known at room temperature, aside from lithium. This is one of the lowest density materials known. So this brings me to a point that I want to try to make, is that COFs are crystalline. As you can see here from the X-ray powder diffraction I'm showing on the right. There's a class of materials that have emerged from using the reactions that we've developed for coughs, but they are not crystalline. They are not produced as crystalline materials. These are called POPs, or porous organic polymers. Now you see this all over the literature. POPs are made under the same conditions as coughs. They are made using building blocks that we made coughs from. And so they are based on the chemistry that we developed in cough. But then there are amorphous, or they are poorly crystalline. And I would say that a POP is really an ill crystallized cough, or a poorly crystallized cough. So in fact, in my group, for every cough that we crystallize, we probably produce tens of POPs, okay? So when your student comes to you with a POP, say you should crystallize that into a cough. So I want to make that point, is that POPs are not crystalline. They are incomplete structures, and they do not represent new chemistry. Their chemistry is based on coughs. They're just poorly crystalline materials that students should go back to the lab, or their advisor should ask them to go back to the lab and crystallize them. So POPs are not crystalline. The other thing about POPs that I want to say is that they're not polymers. Polymers are macromolecules, okay? And they're characterized differently than POPs or coughs. Okay, so it's a misnomer to call them POPs. So I want to just leave you with the following message. POPs are not crystalline, coughs are crystalline. POPs are not polymers, and coughs are extended covalent solids. Sometimes the POP people call coughs polymers, and that's wrong. Coughs are extended covalent solids, like we learned in general chemistry. Extended covalent solids are infinite networks where covalent bonds extend from one side of the crystal all the way to the other end. They're not macromolecules, and they are not interrupted structures. So that's just a note just for, I would say, intellectual clarity about what is a cough and what is a POP. Next, I want to show you a third linkage, and that's, I already showed you triboroxine and boronate ester. Now I want to show you the conditions under which to crystallize imine coughs. Here you have dioxane, same solvent as before, but instead of maceraline, now we're adding acetic acid to help in the reversibility of the reaction. So this is basically to help you form the bonds, and the same conditions. Under 120 degrees C, 72 hours, you crystallize what we termed as cough 300. The structure is 5-fold interpenetrated, we get from powder diffraction. And you can make the expanded version of this, but now with 3 molar acetic acid, okay? And it turns out this one, we are able to characterize this with rotation electron diffraction. Single crystals of cough 320, where the characterization using the electron diffraction was done by Professor Zhao Dongzhu. This was very exciting because now we can get to the atomic arrangement with great definitiveness. Now we can determine that indeed this material is 9-fold interpenetrated and not 8 and not 7, because from the X-ray powder diffraction, sometimes it's not easy to decipher the level of interpenetration. So this is one of the early power of this electron diffraction technique in characterizing coughs. Well, another powerful thing about the coughs that we discovered early on is that you can take a catalyst like this, which is known, the cobalt molecular catalyst is known to catalyze, to convert CO2 to CO. And you can take this catalyst and reticulate it into a cough, meaning to fix it in position and covalently link it into a network, a crystalline network, where the components would be accessible by permeation through the pores. And this was a joint study between my group and Peidong Yang and Chris Chang in our department. But it turns out that because the catalyst is linked into a solid, the deactivation mechanism is blocked because now the molecules are farther away from each other and the active sites are exposed through the access from the pores. And so you get very nice turnover frequency and turnover numbers. So very nicely active material in the conversion of CO2 to CO. But the other thing that I think is very interesting is that by functionalizing the links that, or the linkers that are linking the catalyst sites, you're able to modulate how electron-rich or electron-deficient you want cobalt. In this case, we wanted cobalt to be more electron-rich so that you can have higher reactivity with CO. And so you can functionalize without changing the overall structure of or the backbone structure of the COF or its crystallinity. You can functionalize the linkers and modulate the electronic structure of the cobalt and get to 8-fold increase in turnover numbers. And what this is telling us is that this catalytic center is really electronically wired through the linker, okay, by virtue of having these linkers between them. They're really not just fixed in position in the network, but also electronically wired, and that any change that you make here in terms of the electronic character of this alters the electronic character of the catalytic site. So I think that this is taking advantage of the versatility of molecular chemistry and really translating it into a versatility in a solid or a material. Okay, beyond imines, we can go to hydrazines. I'm going to zip through these, but keep your eye on the conditions. We're using acetic acid, same conditions as the first COFs to crystallize the hydrazine COFs. Also, my former student was successful in crystallizing these borazine ring linked COFs. This is a very nice report from Arnie Thomas's group. They use very high temperature to crystallize these triazine-based COFs. Now, I just want to caution that using high temperature means that we're not going to be able to use functionalities, the organic functionalities that don't survive these conditions. So that's one of the things that you watch out from when you're doing COF chemistry, is that you're trying to crystallize the COFs under mild enough conditions that your organic units can be translated from the molecule to the solid and therefore be able to carry out the chemistry you want in the COF. Imide COFs, now we're using isoquinoline as a catalyst to reverse the reaction and help the crystallization process. Hydrazine or phenazine COFs. This is a COF that was actually developed in my group by Adam, but we wanted it to be even more crystalline than it was, and therefore that delayed the publication. So we were scooped by Dongling Zhang, but very similar conditions to what we've seen before. And not too different from what Adam in our group has been, when he was in our group, has been using. So this happens sometimes in this, fastly evolving field. And we can also make, recently we've shown how you can make urea-linked COFs. See here the high crystallinity of these COFs, as well as Shenfei has been able to extend this by using longer linkers and still crystallize the COF. Also, Shenfei was very successful in taking a linkage like the ester linkages that are so useful in polymers and making MOFs out of them. Here he's using dioxane, not mesitylene, and heating a little bit more for 3 days. So 150 degrees instead of 120 degrees, but these are nice structures based on the ester linkages. Here is more of those. And he even could get an X-ray powder diffraction of a structure as porous as this one. This is one of the largest pore crystals known. It's the linker is made from a series of 10 phenylene units. And so this tells you sort of the range of things that could be done and really the wide variety of metrics that could be accessed. This is a very important cough because it uses an unfunctionalized olefin to make an extended structure. So this cough is olefin linked, and it's entirely made from carbon-carbon bonds or carbon-nitrogen bonds. And these are very strong bonds. So this material, the reason we target this material is that we wanted to make a very stable, thermally and chemically stable structure. But you see here, we're using macetylene dioxane, and this student added acetonitrile, and turns out he needed to use trifluoroacetic acid as a catalyst. So all of this is a result of many, many reactions in studying the conditions under which such a structure could be crystallized. So this is the X-ray powder diffraction. It's a slipped graphitic layer. As I said before, we use IR and NMR, carbon-13, nitrogen-15 labeled NMR, to make sure that the structures, the completeness of the structure. But you see here the stability. This is the cough, the original cough with olefin. This is the same cough with an HCl, 12 molar HCl, saturated KOH. This is the IR of those. And even N-butylithium. So very harsh conditions, and the structure is maintained. The linkages are maintained. This is the sort of stability that we need to be able to use these materials for carbon capture or water harvesting, which I won't discuss too much today. But if you work on carbon capture, you understand that carbon dioxide has to be separated from water. So you really need water resistant. And as you capture carbon dioxide, you're generating acidic media in the MOF, or the cough. So the material needs to be stable under acidic and high, let's say, acidic and basic conditions. Not only can we link organic building units together, but we also can do that to make ribbons, and then take those ribbons. Now this is a solid, take that solid and then add to it a linker that would link those same ribbons together to make a new cough. So I'm just sharing with you the versatility of the chemistry that you could do with coughs and the magic of organic chemistry, of all those many decades of beautiful organic reactions now can be applied here to making extended structures in 2D and 3D. This is another powerful example of how the orientation of the nitrogens around this unit, once we make the imine structure, makes a voided, let's say, grid structure. And this turns out to be extremely crystalline material, and to absorb water from air. And in this case, the air is about 35 to 40% relative humidity, very similar to what you would get most of the year in a desert. But you see this beautiful step behavior, which is what you need for water harvesting from air. And that's done in a cough. You can see also here the reversibility of the uptake and release of water. The material is perfectly stable to water and to cycling the water. The reason I'm showing this example is that the crystallinity of coughs is not just for characterizing the cough, but but also sometimes it's extremely important for properties. If this cough is not crystalline, the water behavior, the water uptake behavior will not be a step behavior. Okay, and we've studied this, let's say in moths, and we find that water molecules crystallize or they form small seeds, crystalline seeds inside the moth. And in this case, the same thing is probably happening, we're studying it still, in the cough. And if the cough is not crystalline, you're not going to form an ordered network of water seeds, and therefore you will not get this step behavior, which is what you would need, this cooperative step behavior, what you would need to make a viable water harvesting material. So the way this framework chemistry works is we call it retrosynthesis of frameworks. You imagine which network you want to make, dissect it into its building units, look at the building units geometric requirements. In this case, the units require 90 degrees. Well, we can then pick the molecules that provide you with that and the linkers. And in this case, 120 degrees and 60 degrees, and that's, you can identify the organic molecules that provide you with those angles. You put them together, simulate the X-ray powder diffraction, then go to the lab and make them. And if you can make them as crystalline materials, you will find that in fact, these units have no other way of coming together under those conditions. So this is an example of how you can take two building units that don't form just one structure, but the possibility is that you could make many different topologies. But let's say I pick this topology. All these topologies are based on linking of triangles and squares. But let's say I want to target just one. Okay, so again, we use what we know from organic chemistry, which is that linkers of this kind. So basically you take the topology, you dissect the topology and you look at the angles and say, well, I need to be able to turn these aldehyde with respect to each other. So I need this stereochemistry where the methyls allow you to have these particular angles, okay? So that you can make the structure that particular topology by putting the methyls here and controlling the conformation of the building unit, and therefore be able to achieve that topology among the other topologies. And that, of course, was done as I showed there, and you can see the X-ray powder diffractions are quite sharp. You can do many other variations on the building units, but as long as you obey the angular requirements, you will make this structure. Okay, so those are the linkages that you can do, let's say de novo, by mixing the appropriate building units together and the linkage forms. And then you're making your cough. But there are some linkages like the amide that don't work de novo. We've tried to make amide coughs and we just could never be able to crystallize them. So one way to do it is to take your imine coughs, which are now very easy to make. They're like, I call them the fruit fly of cough chemists. You can make them very easily and oxidize the imine under these conditions to make the amide. Now, the nice thing about this is that you start out with a crystalline material and you don't destroy the crystallinity by converging your linkage under these conditions to the amide. So this is more or less what you would call a crystal to crystal transformation. And I'll show you the X-ray powder diffractions, but we've done that on the hexagonal structure. And to show that it's more general than just one structure, we showed that in fact, you can do it also on the Kagome type structure. And we, as I said before, we use IR to show the disappearance, let's say, of the imine and the appearance of the amide in both structures. We use NMR to show the disappearance of the imine and the appearance of the amide, same in both structures. And we study their porosity. And you can see here that the imine and the amide porosity differ. We think we're not evacuating the pores as well, but the material is still porous. So we are still working more on activating the material, trying to find those perfect conditions that remove everything that is in the pores. But we have other examples that we publish where the porosity is not affected at all. But in this particular reaction, the amide reaction, they seem to be affected because the amide attracts more, we believe, more water, and these waters are very hard to remove, and therefore the slightly lower porosity. But look at the crystallinity. This is the imine, and this is after it's been converted to the amide. Perfectly crystalline. In fact, more crystalline as you go to the amide. So this is approaching what molecular chemists can do. They can take their molecules, convert them into other molecules, and preserving their overall character. Here we can take our framework, and without breaking up the framework, we can go in and convert all the linkages in that framework to another linkage without destroying the crystallinity and the order of the structure. Obviously, the amide is a lot more stable than the imine, and that was the driving force for going to the amide for us. So this linkage conversion could be applied to many other reactions, as you see here. All of these are post-synthetic conversion of the imine to these different linkages that we cannot make any other way. So this adds again to the versatility of the chemistry. You could do even multiple reactions on a COF. This is a COF that's being converted through several steps to another COF, okay, to make this thiourea type of, or carbamate type of linkage, using multiple steps. So you're taking a solid and you're doing several steps of reactions on it without destroying its crystallinity and getting to a structure that you are targeting. Another level of let's say, sophistication in COF chemistry that could be done is that dioxin is considered to be an irreversible linkage. So how do you actually crystallize that? So we look at the mechanism of such reactions, and let's say you have one component of the reaction, the mechanism that is reversible, and that brings the components together so that they have very little chance to move away from each other. And that would be then, the last step is an irreversible step. Once those components are close to each other, then you can basically join them because they have no other way of getting away from that linkage. And so what I'm trying to say is that the irreversible linkages can be crystallized by preceding that with a reversible linkage that brings the components very close together. And then in the end, as we show here, the ring closure reaction. So that's the conditions under which these dioxin-linked structures form. These are the crystal structures from powder diffraction. And this is a summary of some of the linkages that we have, that we've done and that I've covered here: boroxines, boronate esters, imines, hydrozones, imides, phenazines, triazines, borazines, urea, oxazole, thiazole, amines, esters, dioxin, carbamates, olefins. So a lot of the very important linkages in organic chemistry are represented here. You can also do many, with the fact that the backbone is very stable, so you can do many organic reactions on the structure on the COF, once the COF is formed, and still preserve the crystallinity of the structure. And this gives you a very nice handle into functionalizing the pores with many different types of functionalities. The ultimate, of course, is getting those COFs in single crystalline form. And there again, we use slow down the exchange reaction with the imine. But we do this by adding a competitor to the imine formation. We call it a modulator, which is aniline. Aniline competes in the imine formation reaction and slows down the this imine exchange reaction, and therefore we are able to make single crystals of COFs. You do have to wait many, many days, I think 30 days or 40 days in some cases, to make those single crystals. But once you make them, you don't need to wait anymore because now you know what the structure is. So these are giant, let's say, from a single crystal point of view, these are giant crystals that could be easily characterized or that have been characterized by routine X-ray diffraction in an in-house instrument. So you can see here that as you add more and more aniline, you see that your crystals get larger. So these are the first single crystals of COFs that are amenable for single crystal X-ray diffraction. And the question is, did we get the right structures from the powder? And the answer is yes, we've got the right structure, but now we know exactly the bond lengths and angles. But also in the powder structures, we didn't get what's inside a structure, okay? But now with single crystal, we can say that with COF 300, there is a chain of water molecules that we did not refine in the powder, but can observe in the single crystal X-ray diffraction. So this is the power, of course, of single crystal X-ray diffraction, is that it gives you as much information as possible about the environment in the pore, but as well as the framework. Also, you can carry out this imine reaction by either having the aldehydes here or here. Okay, so you can have aldehydes here and amine here, or amines here and aldehyde here. The type of structure you make would have the possibility of having the carbon here or here. And with powder, you can't tell the difference. But with a single crystal X-ray diffraction, we were able to tell the difference. Also, you could make COF structures that are not the most symmetric possibilities. And so they were not easy to guess. So they're really very hard to guess that they're gonna form. And without single crystal X-ray diffraction, it would be very difficult to refine them from powder, as illustrated here in this hexagonal diamond type structure. Okay, so that's the basics of what we've done in COF chemistry, and now I would like to show you how we can introduce dynamics, not just the stability and robustness of the backbone, but now we can use those elements into creating dynamics by molecular weaving, okay? So I would say carrying out dynamics in this way, like a breathing solid, is not a very healthy way to do it, because as the solid expand and contract, bonds break, and if some bonds don't reform, then the material will break. So I would say this is not a good way to do dynamics, because ultimately the material breaks. However, it's a lot better to interlock things physically, like we propose here, is that leave the backbone intact and not dynamic, and add dynamic units onto the backbone, as shown in these two cases. But the ultimate is that just make the whole framework out of components that can slide with respect to each other without breaking up the structure. So these threads can move away or towards each other without breaking up the material. So therefore you can make a dynamic solid, and that's the reason why weaving is the oldest way of making fabric. And the reason the fabric is still made in the same way that it was done in the ancient times, through interlacing of threads, is that you can bend the fabric and without breaking the fabric down. And the reason you can bend it without breaking is because these threads are mechanically interlaced, or that they are mechanically interlocked. And so they have many degrees of freedom to move around without the structure breaking down or unraveled. Since you're not stressing covalent bonds, but rather you are you're just playing with the physical interaction between those threads. But if you give a student this project, you say, go to the lab and make this woven cough, okay? Of course, the students will either run away and leave the group, or they will just ignore the professor and go on to do something more reasonable. And so then I learned a lesson after telling students to make this structure, and they're ignoring me. Probably, Adam, you remember this, but then I realized that perhaps a better way to introduce the problem to the students to say, hey, we are reticular chemists, and reticular chemists think in terms of building units. So to make this structure, all I need is a building units that has this up and down intersection, right? If I can make a building units like this, then I can reticulate it into what would, in the end, be a woven structure. And that worked. So I said, Yuzhang, can you make such a building units? And she said, it's already been made, Professor. That is the copper-1 mutually interlacing phenanthroline complex that Jean-Pierre Sauvage has made and used to make catenanes. So what she did is that she put the aldehydes on there, and you can tell that she's trying to do imine chemistry. She joins this with these diamines to make imine threads covalently linked, but the threads come together through interactions with copper. Okay, so the only thing linking these threads is just the copper units. The copper units allow the structure to crystallize because they bring those threads at regular intervals, and you make this diamond structure. Okay, so if I connect the copper positions, it would be a diamond framework. And the very nice thing that she discovered is that you can remove the copper. You can add KCN and completely remove the copper from the structure to make the woven, truly woven cough. You can do this reversibly. You can do it as many times as you like. You go from a crystal to a non-crystal, not amorphous, but non-crystal, because anytime I add copper to this, it goes back to the crystal. I know the structure of this, even though it's a non-crystal. And we measured the elasticity of this material, and turns out that it's tenfold more elastic than this metallated cough. This really propels the woven structures into this idea of dynamics, and then how to incorporate these into composites to make very tough materials that can, where these woven units can absorb energy and therefore make for tougher materials. It's highly crystalline structure. We characterize it using electron diffraction and powder X-ray diffraction. And this is, you're looking at an idealized form of the structure. Just for clarity, you can see the blue threads and the red threads interlacing, weaving in and out of each other to make a physically connected structure through physically connected threads. So from a chemist's point of view, this is a one-dimensional structure because it's made from one-dimensional building units that are physically linked. But of course, the overall structure is a woven three-dimensional form. I just want to show you that, in fact, the structure is dynamic because you can put a molecule that's much larger than the pores of the metallated into the non-metallated, okay? This is this molecule trying to get into the pores and can't with the metallated, but when you demetallate, it goes right in. And that tells you that the pores are stretching to accommodate this large building unit. This is the crystal when it's metallated, and this is the crystal when it's demettallated. So this is the non-crystal that I was talking about. The threads are not unraveled, and that's why when you add metal to this, it goes back to this one. Okay, so in the last minute or so, I want to just share with you very quickly how you can move away from the sp2, sp3 linkage, or the common connectivity that organic chemistry gives us, into um, 8 valency or 8 coordination or 8 valency in these COF structures using sp3 building units and infinite units. So, well, that's based on the silicon cube, which so many of us try to link into an extended structure using the building block approach, and not very successfully. However, if you take this unit and you put in, consider the isoelectronic pair, the phosphorus and the boron, then you can see how one might be able to make COFs based on this cubic unit. Okay, this would be a nicely reversible reaction because this reacts with acid or water to have this reversible interaction, this phosphorus, oxygen, boron, this Lewis base, Lewis acid interaction. So we thought this would work, and indeed, great postdoc in my group, Cornelius Gropp, actually this was his idea entirely. First, we tried copolymerizing the boron, the diboronic acid, the diphosphonate, but that didn't work. What worked is that you make a molecule that contains the boron and the phosphorus. And because these are complementary, they come together into the cubic form. Now, there are molecular clusters known like this. And so we are following that kind of chemistry, except now we are successfully extending this into 3-dimension. And you can functionalize the building units, and the chemistry is fairly versatile. You can expand the building units and still make the cubic forms. The thing that reticular chemistry provides you is that the right conditions under which to crystallize this, and the addition of what we call modulators that, like the aniline in the case of imine, that can modulate the kinetics of the system so that you can crystallize, make crystals of these extended structures. This is the powder diffraction pattern, and this is what the structures look like. This polycubane, this is the boron phosphorus linked by the organic polycubane structure. And as I said, you can make the expanded analogs, and you can see that in the X-ray powder diffraction, expansion of the unit cell. And if you add acetic, an acid to it, like HCl, you can turn that cubic structure into an infinite SBU, or an infinite connectivity of boron, oxygen, phosphorus, boron. This is not a unit that is known in chemistry. So, but we are able to trap these units in these COFs by virtue of having a water molecule that's sitting on the boron position, linking the layers together. It's a very, very nice way of making these, in that you take the polycubane, when you add acid, you just basically unzip the cubes. You break every cube into 2 parts, okay? And then these parts come together to make the chains. And this is very nicely, we call it the slice and slide mechanism, where every pair of phosphorus and boron is cleaved from the other pairs in the cube, and then these chains slide with respect to each other to make the COF with the infinite valency. So, well, so that's how you get higher than valency, or higher than 3 or 4, and this is sort of a chronology of the power of the covalent bond, running from the Lewis concept of the covalent bond to the creation of polymers and host-guest complexes, total synthesis. All of this is based on covalent chemistry, of course, the introduction of catenanes. And now all of this chemistry that is based on molecules can be extended into 2D infinite structures, 2D COFs, 3D infinite structures, the 3D COFs, woven structures, and now these higher valency COFs. Okay, well, in addition to the students that I've acknowledged throughout my presentation, I want to acknowledge my current group members and our funding partners, as well as I want to thank you for the invitation and for listening to me. I'd be delighted to answer any questions that you may have.
Thank you so much, Professor Yaghi, for this very nice presentations. Now we have time for questions, so the audience, please feel free to raise your blue hands. I already start to have a questions from Professor Hanadi. So Professor Hanadi, please unmute yourself and you can ask your questions.
Can you hear me?
Yes. Hi, Hanadi.
Yes. Hi, Omar. That was a beautiful, beautiful talk. So many transformative concepts in there and so much beautiful chemistry. I had a question about your the cough based on sauvages, copper bisphenolphthalein. And I was just wondering, are you planning to introduce the type of sauvage machines in there where you have phenanthrene and terpyridine, and you change the copper oxidation state in order to have it switch? And I'm just wondering how that could be possible in a cough system.
Yeah, well, you could do what you're suggesting, but also you could take, because these woven structures also are amenable to functionalization. Everything that I was talking about in cough chemistry could be applied here. You could always dangle those machines onto the framework itself, rather than just have it at those intersections that I showed you. So it really does open up a lot of different possibilities that not just take advantage of the chemistry of coughs and the robustness of coughs, but also the dynamics. You can have the whole thing being dynamic, or certain parts of it that carry out local dynamics. So I do believe that these woven structures are going to be very, very important in terms of the mechanical properties of materials. So this is the direction that we're going. We're studying the mechanical. What do they do? How do they transmit stress, and why our initial measurements on materials, why do they make materials so much tougher than with them than without them? So I think that's the direction where we're going with this. But yeah, I would love to see Savage or Faringa or Stoddard or somebody putting machines in there. We have a lot of ideas along those lines, but not enough students to do all of that work.
Thank you very much.
You're welcome.
So we have also Ehsan that has questions.
Thank you so much, Professor Yaghi, for the great talk. I have a question regarding your outstanding paper in 2005. There in the science paper, you proposed that COF1 shows a AB stacked solid. However, one might expect that AB would be energetically unfavorable comparing to the AA stack, which has like pi stacking there. I would be delighted to hear your comment on that. Also, is there any other COFs with AB stack reported as well?
Yes, there are. You see both. You see AB and you see the eclipse AA, if you will. I think that the AB we propose for COF1 is ideally suited because if you think about one layer having a BOB ring, hexagonal ring, now you can think of another ring that turns to have one boron above one oxygen, so that you have the Lewis acid Lewis base interaction. And I think that that's operating in that structure. I wouldn't say that it's not the most stable conformation. I would say that that's a favorable. I would say that's a favorable stacking. Now, the COF5 that is eclipse is not exactly right on top of each other, because if they are on top of each other, then you have a boron and boron right on top of each other, the oxygen right on top of each other, and that's not so favorable. So what it is, it moves just a little bit. It's staggered just a tiny bit to allow the boron and the oxygen interact, or boron from one layer and the oxygen from another layer to interact. And then it zigzags throughout the structure. That's the basis of that, if you want to call it eclipsed, largely eclipsed, let's say, structure. I hope that answers your question.
Thank you. Yeah, but you mentioned that the boron and oxygen would be on top of each other, right? But in the AB stacked, if I remember correctly, the pore of the bottom layer is going to be on the phenyl ring of the top layer, right? So you mean every other boron and oxygen will be on top of each other?
Yes, yes.
Okay, yeah. Thank you. Thank you so much.
Mm-hmm.
We have 3 other participants that have questions. So Afsin will go first, then Tuan can go after that.
First, I want to say thank you to Professor. I have a question about characterization. In this question, as a student, for example, on my knowledge, the NMR is not the best characterization for polymers. I want to say about it's a very general question, but about the priority of characterization that we can do for coughs.
Yeah, coughs are not polymers. Okay, we have to use the right terms when we refer to things, especially since we are teachers and students. Coughs are extended structures, as I said before. They're infinite structures. They're just like diamond is an extended structure. So keep that in mind when you're trying to characterize them. So I showed that we can do it by powder X-ray diffraction. That gives you what kind of network it is. But we also use IR. IR is a very rough way of saying, okay, you have the right bonds that just formed, whether they're imine bonds or whatever. If you do careful IR, you can potentially get rough estimate of yield, but it's not sufficient. So you have to do NMR, and you have to do, let's say for the imine, you have to do nitrogen 15 enriched NMR to absolutely unequivocally be able to get at the question of yield and the extent of conversion. So we do that routinely. We absolutely have to do carbon 13 and nitrogen 15 NMR. And so the other thing that sometimes you do is you make model compounds that represent those linkages, just molecules that have those linkages in them, and they are quite informative. Whether it's for NMR or other techniques, to tell you whether you have the right entity or not. But ultimately, if you work hard enough, you can get a single crystal X-ray diffraction and get at the atomic arrangement, which, as I showed you, is possible. So I think I would say that the difficulty in characterizing coughs is largely in our head. But in reality, we have so many techniques that I've just showed you that really characterize the cough in the same way an organic chemist would characterize a molecule. Okay, keep that in mind, is that I think that there is no real difficulty here.
Thank you again.
Okay, so the next question is come from Tuan, and then Ashley can also ask after that.
Hello, Professor Omar Yaghi. My name is Tung Doan, a PhD student at UNLab UPT. Thank you so much for your presentation. I have one question on functionality of the material. So, for example, I have a material have low selectivity for carbon dioxide over methane. So, what can I do to modify this kind of material?
I'm sorry, I don't understand your question. Can you just briefly repeat? It's not clear.
Okay. So, for example, I have a material, they have low selectivity for carbon dioxide over methane. So what should I do in this case to improve this selectivity?
Well, I mean, this is not a new problem. This has been discussed extensively in the literature. One of the things, the easiest thing to do is to functionalize the pores and study how this selectivity is impacted by the functionalization. So you could do, for example, studies on the size, the size selectivity, but also with those molecules, you can think about other basis for selectivity. It could be electronic selectivity. You could have open metal sites that select for CO2 because it has lone pairs, let's say, on the oxygen, and therefore they can bind to open metal sites, but the methane can't. You can think of these kinds of things that also discussed in the literature. There's a big literature on co-ops used for gas separation that I encourage you to look at.
Okay,
The next question is from Ashley.
Hi, Professor Yaghi. It's Ashley Howarth. I'm an assistant professor at Concordia University. First of all, thank you for a very nice talk. I'm of course very familiar with a lot of this work, but the stuff I'm less familiar with is your molecular weaving work. So I had a question about your woven structures. Can you comment on how easy or difficult it is to achieve permanent porosity in those types of structures? And do you have to do something special to activate them?
One thing, thank you for reminding me of this aspect, which I completely ignored. When you make the woven structures, you have copper that is bringing the threads together. When that form obviously has anions in the pores. So your porosity is very low because your porosity is based on those solvent molecules that you remove, but the anions are still floating in the channels. So I would say the methylated one always has very low porosity. Now, when you demethylate, the whole thing is like a fabric. So sometimes you get porosity and sometimes you don't get porosity. And trying to prop it open is not so easy. And that's why I don't think of these so much as porous materials as much as they are woven dynamic materials. Okay, but we can use the porosity or access to you have access, as I showed you with the dye molecule. You can use this access to functionalize them. But I really think that the power of the weaving is going to be in the mechanical properties.
Right, because they're just so robust.
How to impact. Right, and those and because they're woven, they're physically woven. Yeah.
And so I guess if I could follow up, you mentioned that when there's an anion in the pore, the porosity is going to be lower. Do you ever try to substitute anions or cations with smaller anions or cations? And can you modify that and modulate that a bit?
And yes, in fact, you can make, it's as if you know more about what my students are doing than I do. Seems like we do. Actually, you're right. We did put in small anions because sometimes they use organic anions to make different forms of weave, because you can make not just a diamond, you can make many different forms of weaving. You can make them interpenetrated, non-interpenetrated based on the size of the anion. But once you make it, you can exchange that anion with a smaller anion and create more pores. That's true. And if you're really interested in porosity and modifying porosity, you can always functionalize your methylated form before you go to the woven form.
Okay, awesome. Thank you very much.
You're welcome.
Thank you. So next question is Mohammed.
Hello, Professor Yaghi. Thank you so much for this nice reticular chemistry presentation. I had a question about the 2D curves. You mentioned that we can design new 2D curves by choosing the reticular chemistry way. So we can imagine some linkage, ideal linkage and ideal conformation to get rise of a particular structure. But most of time, we can get some order sheet, but the way that those sheets can stack is reduce their porosity and useful of this porosity. Do you think that we can use some template to program the way that the 2D sheets in COF can be stacked, there is any way to solve this problem?
Yes, this is a very, very good idea. And like all very, very good ideas, they've been tried and published. Tom Bine in Munich has done very beautiful work at, I guess, I don't know if he calls it templating or not, but at strategically placing interactions, complementary interactions between layers to allow for a design, let's call it design stacking of the pores. Yes, you can, there are many other strategies that you can use if you're willing to go through the specific design that is needed to make those stacks. It's not an impossible thing to do. I think my comment was more, if you don't do anything aside from assembling the building units, you will have some uncertainty in deciphering the disorder between the layers.
Thank you so much.
Thank you, Professor Yaghi. Professor Weiss has a question also.
Hi, Omar. It's great to see you.
Hi, Jim. How are you?
Thanks so much for coming and doing this. I must say, just between the two of us, that it's been a great pleasure for me to be alive and doing chemistry during the last 20 years or so, to watch how you and your group have developed this chemistry. It's been relentless, creative, thorough. I really, haven't seen much else like that in my career. So I congratulate you for that. It's fun to see what you're going to be doing next. Just a quick question. In small molecule chemistry, polymorphism is an important phenomenon. It's widespread. It's sometimes looked at as a problem, but it's also an opportunity because it gives you access to various solid forms. And in many of the COF construction strategies, different types of networks can emerge. What do you use as your rules or guidelines to tell you what to expect? I mean, reticular chemistry looks at the details of angles, but those angles are not fixed. So presumably a set of related structures with potentially similar energies could be formed. How do you deal with these issues?
Thank you, Jim. Thank you for your kind remarks, your initial kind remarks. Yes, we've been there from the very beginning. You were doing those hydrogen bonded, beautiful porous structures, and we were doing other MOFs, and then we got into COFs. It's been a wonderful journey, and it's just the beginning. It's really just the beginning. We just figured out how to make frameworks. Now there's a wide range of chemistry and applications that will emerge. To answer your question about how do we design, the way I think about it is in the following way, both for MOFs and COFs, is that if I take two molecules and I want to link them together, they have maximum degrees of freedom to fall into many different structures. So how do I select from among these? For example, if I was going to link two tetrahedra together, I'm going to make, the potential is for millions of structures to result. And in fact, there are people who enumerated in mathematics, who enumerated those structures. But how do I then, what do I do intellectually to gear to solve this design problem? The way we have been thinking over the last 25 years about this is to say, okay, if I take two building units together and they have maximum degrees of freedom, they will fall in the most symmetric structures. And so if I'm talking about tetrahedra, then I pay attention to diamond. And in fact, and if it's triangles, if you're linking triangles together, you're going to make what's called strontium silicide network. So you could identify those handful of highly symmetric structures, and 80% of the time, you're likely to get what you're looking for. Now, if I want to refine this further, and I really, because someone like you who's very rigorous about this stuff will say, hey, Omar, that's just guessing, and you have a good guess. So how do I then make those guesses better and better? And the way to do that is, one way is to do conformation. Conformation have approximate angles that now narrow the field even further. But ultimately, if you really want to design, and this has worked, by the way, this has worked very well, because combining conformation of the linker design and high symmetry works very well. But it's not the only possibility that could result, right? As you mentioned, to get the only possibility, you need to look at your network and pick that unique combination assembly of building units that would only result in that structure. But to do that, you have to spend a lot of time making your building units, and it's just no student would want to do that.
Yeah, look, I mean, I maybe I would have thought of saying at the beginning of your career that you were a lucky guesser, but after 25 years of the sort of things that you've done, I can't say that anymore. It goes well beyond luck. I mean, but there's one thermodynamic parameter that's important that doesn't like symmetry, and that's delta S. So, and you know, a lot of these syntheses take place at elevated temperatures. So there's a factor there that, you know, is working against you if you use symmetry alone as your criterion. It's a subject we could talk about at length.
Sure. But I think that all these tricks about modulator, all these things, the right solvent combination, all these things are trying to overcome. Basically, you're trying to do what nature does not want to do, okay? And you know, to overcome this thermodynamic issue. So keep in mind that a lot of these building units, they're very directional, so they're not really as free to do what they want as we like to think. Okay, so already by choosing those linkers, you're eliminating the vast majority of possibilities. Yeah.
Okay, great. Thanks. I hope we see each other again soon.
Thank you, Jim.
Thank you, Professor Yaghi. If you still have a little bit of energy, we still have one question from Masa.
Yes. Hello, Professor Yaghi. Thank you very much. Do you hear me?
Yes, we hear.
Okay. Thank you very much for this nice talk. My question is very general. Could you please also comment on the thermal stability of COPs in comparison with MOFs?
Well, they're stable up to thermally stable up to 300, 400 degrees C. Same thing with MOFs. And they're both made, I mean, MOFs, even though they have metals, they're made from organic. 90% of them are organic. So very similar thermal stability. Yeah.
Okay, thank you very much.
Well, I think any questions from the audience? If 1, 2, 3, if not, please join me to thank Professor Yaghi for this very nice presentation, exciting work, and hopefully we will see more about this subject in the near future. Professor Yaghi, thank you so much to accept my invitations for this QCAM e-seminar. It was a pleasure to have you with us, and we hope to reconduct this in the near future.
Thank you, Adam, and it's a pleasure to see many good friends in the audience, and I look forward to seeing you face to face soon. I hope soon, very soon. Okay, take care.
Thank you.
Bye-bye.
Take care. Bye-bye.
Bye-bye. Yeah.
Mohammed.
Yes, Professor.
Can you just please let me know if I'm recording now? After finishing to record, how can I save it? It's automatically saved?
Yeah, There are
Just
windows that will appear and that will show you where is the emplacement of the recording.
Okay, so it's automatically saved, right? Can you just confirm? I didn't hear you well.
Yeah, Professor Tan?
Yes.
I want to ask something about recording. Can we access to the recording file?
We will share the organizer will give you information. So I'm just collecting the data and then send to the QCAM organizer. Okay.
Thank you.
You're welcome. Bye. Peter. Bye bye.